Hello, I'm Ben Benkowski, a hydrogeologist with EPA in Atlanta, and I'm glad to be participating in this training event on high-resolution site characterization. The module I'm going to present on is the on-site screening tools and methods, and this segment's supposed to last about an hour. Got lots of slides, so let's get to it. So starting off, we work for similar organizations. The US EPA and the Environmental Protection Administration of Taiwan both have laws passed about 10 years apart that require the investigation of the nature and extent of the soil and groundwater pollution at our sites. So we have a legal duty to investigate this contamination. I think that as environmental professionals, it is our duty to develop an understanding of the site using cost and time efficient methods that produce defensible data. So with that, this presentation will cover high resolution screening tools and method that will aid in making efficient decisions about site conditions and remedial actions. So these are the modules that, these are the main topics that we'll go through in the course of this presentation. Some technical resources, a variety of tools, and since I started out with a fairly large presentation, there are extra slides after the end of this, I think, hour-long presentation that I encourage you to take a look at later, because they just didn't make the cut for the 1 hour, but they're all still good information. So the first one that I think is a technical resource for folks anywhere in the world, really, are at our EPA's Clue In website. So this is technical information about innovative treatments and characterization technologies. So you can see all these blue boxes across the middle of the screen here. Those all have pull-down menus, and you can talk about, you can find out about all sorts of those particular contaminants or the strategies that we've got going or the various training events. So I encourage you to go into this website. The second one here is actually, you say it as CERTIP and ESTCP. These are government-funded environmental research programs. Seems to be mostly run by the Department of Defense with participation from the EPA and the Department of Energy. And they run full-fledged research projects. There are currently 250 plus active research projects on their website and on nearly 500 completed research projects. So that's a tremendous resource of high quality, research that's available for you to apply to your particular situation, maybe. And also to help understand certain concepts, they've developed what's called this EnviroWiki, developed by the same people, but has really high quality articles written by invited experts, and I know there's another link for you to pursue. So there's a third organization called the Interstate Technology and Regulatory Council, ITRC. And this is not really directly a government-run organization, but run more by the states with participation from public and private sectors in all 50 of our states and the District of Columbia. So they actually have 52 different topics for the documents that they have produced that are available here at their website. For example, there are these pull-down menus that you can check out about the geology or the chemistry, bedrock or unconsolidated environments. I think one of the things we're going to talk about maybe in a different case study or maybe later in this presentation, is about their fractured rock tools. So just as an example, this is just the first item from their website spreadsheet on ground penetrating radar. You click on that and it gives you the description of the technology, the data quality and applicability and advantages, plus the limitations and difficulty. And for this subject, there are 10 references that you can pull up and learn about ground penetrating radar. And I think there are nearly 100 of these when you look at them on the website. So the other one to look at is provided by the USGS. So the U.S. Geological Survey is very similar in structure and mission areas as the Central Geologic Survey for Taiwan. We both are interested in understanding the geology of our particular areas and how that applies to resources that are available, natural conditions, the hydrology, a very broad range of topics. Both of us are fortunate to have a government-run organization about the geologic resources in our countries. So they actually have, in this particular thing, a fractured rock toolbox, like that one from the ITRC, where you go in and look at it, and it will tell you the various tools and ideas to use when you're looking at, well, in this case, it's just fractured rock, but they also go and do field investigations. I've used them on sites in North Carolina to run geophysical logging in our fractured bedrock sites. Top quality, top-notch organization. And I recommend you browsing their website. So this is their fractured rock tool. You go in here and you identify the various parameters that you have about your site, your goals, and then it will give you some suggestions about what has the best applicability, what's a relative cost. No sense having to figure this stuff out yourself when someone else has spent considerable time and effort to make it easier. So I recommend all 4 of those resources to delve into topics that are, we've only got an hour. We got lots of slides to get through, but those other these 4 resources will be great for your future review. So the first talk about the individual tools will be for shallow, unconsolidated environments, starting with soil coring. So essential information that you should receive from cores is both geologic and hydrogeologic features, a variety of properties depending on what your interests are at the site, understanding about essentially the permeability so you can understand the contaminant and mass distributions, and then also those same contaminant concentrations can give you some gradients, and understanding then once you get those 4 basic understandings, you can come up with some understanding of the effectiveness of how the various remedial technologies can work on, say, a clay-rich area that has a lot of VOCs, or a very sandy zone that has a lot of creosote in it, or any number of things. But coring is really one of the basic steps. My first job was working in the field, actually seeing cores that came out of the ground, and there's just something about physically seeing the rocks that you're investigating. So things that you need in a coring tool, it'd be really great if you could get 100% recovery. You got to be able to know exactly what depth it's from, which requires coordination with your drillers so that you really get an understanding of how deep that sample is from, because you're going to need to correlate that with the ones from other parts. Plus, you need to be specific about the depth to more than the foot, hopefully to the 100th of a foot, because sometimes that makes a difference. You'd like the samples to have a minimum disruption of as you bring them to the surface and retaining the pore fluid, so you could then actually, if you want to, sample them and then send that off for analysis. Should be as the one you see at the surface, the samples you see at the surface should be as close to subsurface conditions as possible. And no, I won't be reading all the slides. Here's a photograph of a core cut in half. You can see these various beds, some very fine grain. I mean, this is a matter of, these are inches and centimeters here at the bottom. So you can really see, like in this case, you can see this little offset in the bed. That permeability difference might make a difference in how the NAPL or the contamination moves within an area. So this level of detail can be important, because it all moves from pore throat to pore throat, from between the sand grains. So it's important to have high quality data. Here in this particular case, in the middle of this fairly thick clay, I believe that's centimeters at the top, you'll see that there is a little tiny sand zone, and that sand zone was treated with a dye that turns red when there's DNAPL present. So in the middle of that big fat clay is a little zone of DNAPL. So it's you would have missed this if you hadn't had a continuous core. So how can you, what are the methods you normally use to get cores? For deeper zones, sonic seems to be the best, because it's, for unconsolidated zones, I've collected sonic cores down to 200 feet before. Rotary has more a thing called the split spoons, and it's, the cores are in a little better shape, but sometimes the production is a little slower than with sonic. But sometimes the conditions are that you need to use the rotary, because oftentimes you have to use water with the sonic, and that can dilute out in your samples, could dilute out the fluids in the core if you want to take some representative samples. And then for more shallow and less consolidated or less indurated zones, you can use a direct push rig to just push the core barrels down into the ground. These are those split spoons that I spoke of earlier. This is with the geoprobe. This is also with a Shelby tube. That's usually done with the rotary methods. These are all single rods that are just pushed in the ground. The dual coring, I think, is probably a better way to go these days. There are, you put in an outer casing which stays in place, and then the core barrel is tripped in and out of the hole. It's better because you get a more intact core, and you have less contamination from sloughing in the hole. You get better recoveries. In this case, this guy is using a special tool to split the plastic casing around the outside of the core. And you can see you get 100% recovery with this. So you can also, the Sonic rig also does these dual core process here. Because there is a big tool that runs the casing down to a certain depth, and then the inner barrel vibrates this core, the inner barrel, down to the 10-foot zone. Usually it's about 10 feet. In this case, they got back 8.5 feet of core. But it was able to give continuous cores for, down to 315 feet deep, which is really, that's a lot of characterization that you have essentially a complete record of the sediments from when you start to when you finish. So problems with some of this, because you're using this vibrating equipment to advance the casing, sometimes it just disturbs the sediments. If the sediments have a very high amount of sand, it's more susceptible to disruption. If the formations are too dry, then you have to use some water in order to advance the tools, keep things from sticking, and that can dilute any of the water, any of the fluids in the core, and you'll get reduced concentrations for any VOC samples that you collect. And it can be highly disturbed. It doesn't have to be. I've seen cases where it's come out just fine. Maybe you'll lose a foot or so, but maybe on the big scale of your investigation, having a 90% recovery would be okay, because you'll get very good data off of the samples that you do get. You can get grain size analysis, you can see sedimentary structures, you can see siltier zones that might control the movement of NAPL. But in general, cores are some of the best information you can get to actually see what's in the subsurface. So this is an example where the water usage really diluted out the TCE that was in that zone, particular zone. This is the groundwater samples later, once the well was installed, but the water sample collected from the pore water of the Sonic core is about 2 orders of magnitude less than the groundwater samples from the well installed in the area. So again, it really becomes more of a screening tool that when compared to a monitoring well, a permanent monitoring well. So the next subsection is about hydraulic and chemistry profiling. So the first tool to talk about is a cone penetrometer. So the cone penetrometer will give you a continuous stratigraphic or lithographic profiling. It can be part of a tool system that's put in place. This needs to go first in the hole because the pressure on the tip is compared to the friction on the sleeve on the side of it. And that's how it makes its determination of the lithologies. So it generates data in real time. It's been used in Taiwan. Here's the paper which talks about the liquefaction from an earthquake. But it is a static push, but you get continuous high quality data. Here's an example of the truck that they come in, and these usually have a hydraulic rig inside this truck, but then it's all contained out of the weather. And this is two examples of the cone penetrometer. This is the tip, that's the sleeve. These are the two strain gauges that record the forces from those two. And this is usually a water porous, so you can get the hydraulic pressures, the water, the pore pressures at depth. So in this case, you can see the sleeve stress is plotted across from the tip stress or pressure in PSI. That's converted to a ratio, and then you can correlate that with the soil behavior terminology. So this readout here can then give you the lithologies that you get in the subsurface from pushing this tool through those zones. And the pore pressure pops up when you're in this clay zone here, and you can get that reading as well. So soil behavior type, excuse me, I had that wrong, but you can see that the sleeve friction on the x-axis and the tip pressure on the y-axis, and those two values plot out to a sandy zone or gravelly zone, a very stiff clay. Anyway, it's a very useful tool, very basic. It was developed by the Dutch, which is not surprising given how much land recovery they try to perform in the Netherlands. But that's where it was developed, I think, shortly after World War II. Very good for lithologies. So there's a couple of versions of the hydraulic profiling tool. In this case, this is without sampling, but it's a continuous profile. You can describe the hydrostratigraphy based upon water that is pushed into the formation, and you run it off of a direct push rig as well. So here's the example of the tool. This is the zone little screen here where water is pumped into the formation, and there are some gauges that understand how much water is going in, what the pressure is. So this is the setup for the equipment, the computer, the controller for the pump, and then the pump itself. And what you get is, this is the pressure of essentially the water pressure of the water being pumped into the formation. This is the flow rate. This is the corrected pressure, processed somehow afterwards. And then from this information, you can get the estimated hydraulic conductivity on this curve here. And you can see, this is the top of the water table, and then the hydrostatic pressure increases as you go with depth. But then you can see this zone here that's got a fairly high hydraulic conductivity, and these little other zones here, then you can match this up with the electrical conductivity and help you understand the hydrogeology of this with this tool. Again, this is the cone penetrometer data, the pressure data, and the electrical conductivity, and you can see this, like this zone right here has low electrical conductivity, low pressure, and a low friction ratio. So this is probably a sand unit from this 10 to 13 foot interval here. It's the laying out logs in in a horizontal fashion, so you can make a little correlation between the three of them, or however many you happen to have. So this is the same basic tool, but then with a water sampler associated with it. So this is a schematic of the groundwater sampling version of the hydraulic profiling tool. As you push the tool in the ground, it's injecting water at 400 milliliters per minute, advancing at about 2 centimeters a second. If you see a zone that you're interested in sampling, you're then able to stop the probe, purge the system of the water that was injected, and then collect a sample that is then pumped with this bladder pump up to the surface and into your sample collection, into your sample bottle. This is a separate one here where there's a direct push tool that you push into the ground, and then it exposes a screen that you can then just leave there. I believe they're disposable. No, removed following the collection of each sample. But then that gives you a screen interval for collecting a sample with a peristaltic pump. So there's a different system called a Waterloo profiler that's got, like many of these systems, tools that go down the hole, lab equipment in the trailer, and computer equipment to store the data that are collected from the process. So again, there's the point and the samplers. So this is the way it was, 25 years ago. But now the more advanced tool is improved with screens, and I'm sure based on their feedback through the years. This is a schematic where you actually push it down, and then you're able to adjust the tool from the surface and then collect groundwater samples. I mean, this is all very, inch by inch, centimeter by centimeter, if you want to characterize to that level of detail. This gives you that high resolution data by using this kind of equipment. This is the schematic of how it works, where you have a compressed nitrogen that comes down, works as part of the profiler, and then you can switch it to sample, and it draws the fluids out, and you put them into these bottles, and you can actually then, I think, do these fill parameters, which are often so very important to understanding the information about the characteristics of your, is it low dissolved oxygen? Is it a negative oxidation reduction potential? All this is really important for understanding your aquifer characteristics and what's the state of your contamination. And then you can use the water samples that are collected with their on-site lab. This is an example of their cross-section where the chlorobenzene concentrations are in the red, but the hydraulic conductivity zones are in this brown line that pops out through here and here. So this is an example of the data you'd collect, and then a few of those in a row gives you a stratigraphic interpretation as well as concentration data for your understanding of the extent of contamination. So this is, again, a couple of logs set across from each other. The membrane interface probe data with the photoionization detector, the index of hydraulic conductivity from the Waterloo profiler, and then the concentration of those of TCE and 111 trichloroethane. You see they're pretty high in this higher conductivity zone, and still pretty high in this lower conductivity zone. But then there's less of it as you go further down the hole, and as the formation probably fines into a finer grain, a fining downward sequence. This is an example of using these multiple tools to give you foot by foot or better resolution for your contaminant distribution. So it's really one of the things that's been developed in the last 5 years or so are these very high quality field gas chromatographs. This is not a commercial endorsement, but it saves a lot of time if you can actually get high quality data in the field while you're doing your work. This is one model called the Frog 5000. If you look at it, from the front side, it sort of looks like a frog sitting there. It's very lightweight, and you can use it. I've used it on my projects, and you get high quality data in a short amount of time. Another tool is this HAPsite, and it's the same. It's a different tool, but it has the same outcome from our interest in that you can get high quality analytical data in the field that's used for real-time decisions about, are we finished going deeper? Do we have it delineated in this particular direction? I've had folks that use this on sites that I'm involved with. So yes, both of these I can recommend as a way to get high quality information to make some decisions while your crews are in the field, and you can then have them keep working in a particular direction. And you can say with confidence what's going on. So these are some qualitative tools for discussion here. So this is the membrane interface probe, which I talked of earlier. So there's this Teflon membrane that warms up, and a carrier gas. As the membrane warms up, the VOCs in the groundwater are then transmitted through the membrane and into a carrier gas, which is taken up to the surface and first through a photoionization detector, which is just a general all-around total VOCs. And then you could have any of these other three, which are more specific and give you better readings, better specificity. You can actually be a little more specific in your results. And then this electrical conductivity, that usually correlates to your lithologies. So, between the two, you can get a pretty good idea of what's at a screening level, what's going on at your site. This is what that setup looks like. Pretty similar to others in that there's a direct push rig. There's a truck that has this equipment inside of it. This is the tool. That's the little window that warms up and that's being pushed in the ground by this operator. And this is the readout that you get from a particular boring log. Here's a little better closer view of that same boring log. So you can see the electrical conductivity on this scale doesn't really show a lot. So the PID, photoionization detection, shows this amount of deflection. but the electron capture device, the ECD, shows a much bigger response. And then the electrical conductivity is a smaller number. But you can see this is the rate of penetration. It goes in and it stops, goes in and it stops. You could do this every foot or so if you had the time, or if you had a particular zone where you needed higher quality, greater data density. But this was one of the first one of these subsurface tools that I ever saw at work, high resolution tools at the Kennedy Space Center in Florida. And once we started doing this work, we pushed the tool down in the subsurface, and there were these little silt layers that showed up on the electrical conductivity readings. And we stopped right at the top of those zones, ran the MIP here, and got these big hits on the PID. We were able to find a whole series of these little silt zones with high concentration zones right on top of the silt. That investigation with this tool led to a complete change in the approach at that particular site. So that was 20 years ago, and I still think it's a great tool. So you can certainly get vertically continuous data. You can do a couple hundred feet a day. You need to worry about things that you might cause you not to be able to get to depth. You get a rocky condition, you're not going to get good penetration, and there can be some lack of resolution of the data, because there is some drag down, especially if you have a high contamination zone. Remember, it's screening level data. It's not like the same as a permanent monitoring well. The other thing is that the compounds that are heated, they volatilize at different rates. So then they come up to the analytical equipment at different times, not unlike a little chromatogram. So if you have a zone with naphthalene, it's going to get there a lot slower than a zone with PCE in it. And you need to know your site and take that into account in the rate that you allow, the time that you allow between where you push and activate the sensors. So this is an example of that, where the actual soils data here in the multicolors are compared to these other zones, and where the membrane interface probe is a couple of meters off from comparisons to the actual soil analytical data. In the grand scheme of things, a couple of meters won't make or break a project, but it does give you an understanding of that there's a hot spot down there, even though it might actually be a meter or so in a different direction. You'll come back through and take some soil samples and nail it down, or take some groundwater samples and nail it down. So this company in North Dakota developed a thing called a laser-induced fluorescence tool. It works for aromatic compounds. It detects NAPLs. Again, it's a direct push tool. And when you push it through, depending on the compound, you get a different reflectance you get a reflectance at a different wavelength. So whether or not you're pushing through what might be petroleum as an L-NAPL or a D-NAPL of creosote, You need to have a different tool and you'll get a different response, but all that is understandable with these particular tools. There's the UVOST that works on, mostly petroleum products. The Targost, which works on creosote, and the rapid optical screening, which works on fuels and oils. And their website's got a lot more of this information on it, but just understand that, once again, there's a tool. It goes on a direct push rig, and it sends the information back to the trailer, or in this case, the shipping container that has the computer and the control equipment, and then this computer over here, which actually saves the information from it. So this is a readout of the log. So you should understand that when these tools get pushed in the ground, there is a laser that is projected out into the formation. And napples, L napples or D napples, will fluoresce at a certain frequency. So they shine this laser with a very specific wavelength out into the formation. Then it records the wavelength of the reflected light that comes back, of the induced fluorescent light that comes back to the sensor. So these wavelengths, this is very specific about the different types of compounds. Understanding them is almost as much of an art as it is a science. I highly recommend that you go to this website down here and learn their instructions on how to interpret these. But you can see, you get these really strong indications of where the napple is, how it's distributed through this zone here. Especially if you have some other information in the subsurface, you can match this up and really learn where your source areas are. They have another relatively new tool, which again looks on the laser-induced fluorescence and the wavelength of that light that's induced. In this case, there is an injection of a fluorescing hydrophobic dye. As the tool is pushed into the ground, this dye is continuously ejecting a very small amount, and when it runs into one of these napple zones, the dye adheres to it and then is available for the fluorescence. Once you keep pushing this down, this little window, this little sapphire window, will come across from this zone here. The laser will hit the dye, it will fluoresce, and then the data will then go back up to the equipment in the trailer. And so you can get very detailed information. This is the general log, like how it was on one of the previous slides, but you can process the signal to just only show the DNAPL signals. And so this is less than resolution, better than 1/10 of a foot or better than 3 centimeters. But you can see this around this 34-foot zone. This is an area that you'll want to concern about regarding source area remediation later. And even down here, there's this one little, 3 centimeter zone at 67 feet. Probably this little zone right here. Now, is that going to be a big enough problem to cause you a very long-term groundwater problem? You'll have to understand. You'll have to sort of learn about that and see what the dissolve phase concentrations are in that area. But it's but for the resolution, it's a a spectacularly useful tool for source area identification. That's the dye, LIF is what it's called, because the dye is injected and it's laser-induced fluorescence, and you have a level of detection around 1% or a little less of DNAPL pore saturation. Now, they say here that you can get maybe 400 feet per day, and if you did shake tests with oil red O, which is the hydrophobic dye that turns red, that's equivalent to over 12,000 shake tests. You could never do that in a day, certainly. But you get, what's that, half a centimeter spacing. That's very high resolution data. I don't know if this is available overseas, but Randy St. Germain, the man who founded and runs the company, is very amenable for technical discussions, and I found him a useful partner in trying to understand things. So, tools for fractured bedrock. We've got some stuff that we're going to cover here, but also some of this is covered in a case study in the other methods part of the schedule on day 2, where I talk about an investigation that I did in North Carolina that it sort of helped me understand the process that I think gives you the best understanding in fractured bedrock. So in general, if you have a source zone where there's DNAPL into a fractured rock zone, it goes down here into these fractures. Some of the DNAPL sorbs into the rock matrix, some of it turns into a dissolve phase plume, and really there's no good way of knowing from the surface where your contamination is. It's basically you need to drill some holes and run some logs down some borehole geophysics and sampling equipment down the holes in a certain sequence before you can really understand which direction your contamination is going and what's the nature of this fractured rock aquifer, if it's metamorphic or if it's a sedimentary like a fractured limestone. It's generally the most difficult zone that we have to deal with in our profession. So this is actually a borehole tool matrix. The ones I've highlighted in yellow are the ones that I prefer. But you can see the various bits of the types of information available on the left and the tools that you can then use to understand that information, and then the secondary use. And anyway, I'll leave this for you to study later as you try to map out your next fractured rock investigation. So there are 4 or 5 technologies here about multi-level systems for fractured rock or other settings. The simplest is just a nested well where you have one borehole and a couple of different pieces of PVC casing set at different depth with the right amount of sand pack and grout between them. But these others are a little more complicated. So for the Waterloo system, it's a series of packers and casings and sampling ports that you install at depth at specific intervals that you may have identified previously with your investigation techniques. The multi-level system, it actually comes as a PVC, not PVC, but a flexible plastic tubing, a polyethylene, that's divided into separate segments that run the whole length of the tubing. I've used them more in coastal plain settings than I have in fractured rock intervals. But you basically go down to a certain zone, cut a hole in the side of the pipe, wrap it with some screen, and then that becomes your sample depth. And all of that is run off one single about 2-inch piece of polyethylene tubing. So here's somebody putting one of these together. You put some centralizers on it. It's all laid out in a row here. There it is being run into the well. And in the end, you have these little samplers that go down into these 6 different zones. I think maybe the 7th is possible. But that gives you a lot of information out of one borehole. The West Bay system, again, is a series of packers and samplers and have various ways to control this from the surface, but you can then set this as a permanent well to sample individual intervals. The flute system is a flexible liner. That's what the FL stands for. It's this goes into a hole, into the borehole, and you need to specify the depth that you want the sampling ports made into this fabric. But it allows you to then pump from this, say from this particular interval here, through connecting up the plumbing up at the surface. So here's an example of it going into the ground, into the borehole, and you attach it to the top of the well, and then you start putting some water on the inside of the tubing, and the material just flows into the borehole. But because it can go in at a specific rate, there's an interesting development here, is that as the tubing as a flexible liner goes into the bedrock, it has to displace the water that's in these fractures. The more transmissive the fracture is, the quicker the liner goes past that point. So you can record the velocity of the liner going into the hole and correlate that with the transmissivity of these individual flow zones, individual fracture zones rather. So, this is a very high transmissive zone. This might be where most of your groundwater is coming through, but this may also have the same levels of contamination, but just not nearly as transmissive. So it's an interesting idea. One of the things you can also do with it is you put this this felt activated carbon on the sides, and it wicks dissolved phase materials into it. Then you can cut those out and send those off for analysis. Or you can do that with NAPL and dissolved phase, and then you can send it off for analysis. Or one of the other uses of this is if you have a borehole that you need to seal, but you haven't had a chance to design the well to go in there, then you can use this to go into the hole and seal off the formation so you don't get cross-contamination. So for some non-depth specific activities, you can use passive diffusion bags. It's fairly simple. You just drop it in the well to a certain depth, and it relies upon maybe a 4-week time period for the water that you put in the bag to come into equilibrium with the water that's moving through the well. So it doesn't generate any investigative derived waste when that's one of its big advantages. And it's a fairly labor simple kind of a process. The other thing is these passive grab samplers. This is a thing that you can activate by pulling a cord, and it pops open a sample bottle that then fills and then shuts. And this is actually one that goes down to some depth, and then the water, when you pull it up, it fills the hydro sleeve fills with water. It's kind of like a one-time bailer for collecting water from a specific depth. So for groundwater surface water zones, it's one of the things I've learned in the last 10 years or so, that all the groundwater usually goes to a discharge to a creek someplace or to a big river. So understanding this transition from the groundwater to the surface water is becoming an avenue where it sort of expands your hydrogeology notion. And it's useful for both screening and you can get very detailed levels of understanding because you can work on really short intervals for your sampling. Using this is just a hand probe. It's about 1 meter long or almost 2 meters long. And you have little slots in it. And you push it to a certain depth. And then you can put some tubing down this probe and collect a water sample from the transition zone in the sediments of adjacent to a lake or in a creek. But it's a really simple way to get depth-specific data. And it really all depends on how much further down you push it. If you wanted to get a 20, 40, 60, 80 centimeter sample, you certainly can. So this is a pretty interesting thing, an infrared camera that's using thermal imaging. The technology has really come a long ways. It's handheld. You can mix videos, take still photographs. I used it, again, provided by the U.S. Geological Survey at this site in North Carolina. And when this orange stripe here is this vine that comes across here. And you can see the cold water coming out of this very specific location. Well, when you look at it in visible spectrum, there's a crack right there where the cold groundwater is actually discharging from a point discharge, and you can see a 4 degrees difference between the surface water and the groundwater. Next slide is actually taken. This next slide is actually taken in the winter time, more of a diffuse flow, but again, you can really see where you should take your sample if you want to understand the concentration as the groundwater discharges and then mixes into the surface water, and then maybe take a sample, 5 meters downstream to see what the average concentration might be after the mixing zone. But it really allows you to pinpoint specifically where the groundwater is discharging. So a distributed temperature sensor, they're fiber optic cables that are laid out, could be, great distances, up to 30 meters in length. Anyway, there's quite a number of configurations. You can get a spatial resolution of about 1 meter, but the thermal differential is down to 1/100th of a degree of Celsius. And because it's run basically with a laser tool in a fiber optic cable, you can get very high quality, high resolution data. So this is some of these cables being laid out before they're going to be deployed out in this lake here. I think this might actually be Lake Michigan, but there's a USGS story about that. And you should, if you want to really delve into the science of how these things work, there's a great article on Wikipedia for this. Look it up. I won't butcher it by saying it here. But you can get really good detail, but you can see in the stream, like in this particular situation, in a stream, you can see the cold water discharging at certain specific places here where the groundwater is discharging, and then out into the pond where the spring is. But then these are places that you'd want to go back to sample for the groundwater discharging. But you can see the temperature is very high resolution over a matter of meters. Here's an example of some of it done in the field along the length of a creek, some older data, and then this connectivity survey data. So anyway, I believe that's the end of my presentation. There are indeed quite a number of other slides after this, which I encourage you to take a look at later. But I'll close by saying Shay Shay and Wen Ti.